Hello everyone, thank you for joining us today. My name is Madam and today we're going to be looking at work done. So we have a few learning objectives and that's to be able to define what work done actually is and to be able to understand what changes the work done on an object and also to be able to recall the work done equation, which is work done in joules is equal to force in newtons multiplied by displacement in meters. So that little s, it's not seconds, it's displacement. Okay, so now actually let's start looking at what work done really is. So you can see here I have a definition for you for work done. So anytime we apply force to an object over a distance traveled, we are doing work upon the object. Okay, so there's a few key words here. Now, what you can see our sort of like misshapen person here is pushing a trolley. We can see that the force applied is in this direction, and from the sort of like triatracks we can see that the distance traveled by the object is also in the same direction. So let's do that, distance traveled. Okay, and this is a very key point of work done. Whenever we're doing work upon an object, the object has to sort of move in the same direction that we're applying the force itself. So say we were to take a box on the floor, right, and you were to let's draw our person, okay, and you were to take this box and you were to pick it up. What you're doing is you're applying force upwards and the box is also moving upwards as well. So what you're really doing here is you're doing work on the box against gravity. Okay, because it's gravity that's the force that's actually keeping the box stuck on the floor, right? So when you're pulling it up against gravity, you're doing work against gravity. Same with, let's go back to our trolley example. When we're pushing the trolley forward, what we're doing work against is the friction between the tires and the actual floor itself. Because think about it, right? If we had no force of friction at all, everything would just be slipping all over the place, right? Like my monitor that's here, it would just slide right off. I would slide right off my chair. It's friction that's the force that keeps things stuck together. So when we apply a force to move an object, what we want to do is overcome that friction, so we do work against it. Okay, you're going to come across this word again and again, and students really get confused because they don't have a solid understanding of what doing work actually is. Okay, so now let's actually have a look at our work equation. Okay, so now let's have a look at the actual work equation itself. So work done is equal to force multiplied by displacement. Okay, I know we've been talking about distance here, but remember we've been talking about distance traveled. We're talking about the magnitude, how far you've gone with the direction. So we're using displacement here. Now you might also see sometimes work done equals force multiplied by distance and a little asterisk saying distance traveled in direction of force applied. Okay, either way is fine really, because a distance traveled in a direction is displacement, so we can sort of skip this extra words if we just say displacement in the first place. Okay, so now let's have a look at the actual units of themselves. So work done is in joules. Okay, we can think of it as a sort of like energy. It's really the energy expended when we apply a force to an object. You can think of it like that, but we just need to remember that any sort of energy is always measured in joules. Now our force, any force no matter what type, is always in newtons, and our displacement is again in meters. Okay, so this is really how we can use the work applied equation. So now let's look at two factors that will really affect the work done on an object. Well, let's look at our force a bit closer here. What sort of force is it? Well, often when we're moving an object against the force of gravity, right? So we're really looking at the force of the actual object itself, which is the object's weight. Okay, so let's deconstruct the force here, because remember, weight is a force and that equals mass times by gravitational constant. Okay, so what we can also say is F equals mg. So really, let's write here mg, or rather weight. So if we have an object with a higher weight, or rather I should say a larger weight, we need more work done against that actual, so we need to provide more energy to that actual object to make it move, right? So we need a greater work done for a larger mass. Also, if we want to move a object a further distance, we need either a larger force or greater amounts of work done. Okay, so you can really see here that the relationships between work done on force and work done on displacement are like this. So let's do here, work done equals force multiplied by displacement. For a constant force, we can say that work done is directly proportional to the distance. If we go double the distance, we get double the work done. Now let's have a look at force. If we have work done is equal to force over distance again, sorry, displacement again. For a constant distance, we'll get, for double the force, we'll get double the work done. Okay, so you can have a look at these two directly proportional relationships. Okay, so now let's have a look at a worked example. As always, we're going to highlight all of our keywords. So figure 1 shows a skier using a drag lift. Okay, so we're talking about skiers going up mountains. So the drag lift pulls the skier from the bottom to the top of the ski slope. The arrows A, B, C, D represent forces acting upon the skier and her skis. Okay, so first of all, let's label some of these forces just for a bit of practice. Okay, so D, we can see is the force parallel to the actual slope of the mountain itself. So this is our mountain that we're on. We can see that D is pointing up, and we know that the drag lift is pulling the skier. So this is the pull from the drag lift. Okay, so now what's B? Well, B is going from about the center of the skier downwards. What force is always acting downwards towards the center of the earth? Well, that's weight. So B is our weight of our ski itself. Okay, now whenever we can see that the force C is going from upwards, from a parallel to the actual surface, the contact point between the skier's C's and the mountain itself. Now, whenever we have some sort of contact between one medium and another, a medium is just a fancy way of saying stuff, right? We get a normal contact force. So C is our contact force, or rather normal force. It doesn't matter how you say it. Okay, contact normal. Right. Now A, we can see A is directly opposite to the pull from the actual ski lift itself, and it's at the interface. So that, remember, that's the point where two different substances meet, between the interface between the ski and the mountain. Okay, so we can understand, right, that the skis are going to rub against the mountain. Whenever you get two objects rubbing, you get friction. So this is not the friction force, the drag force. Okay, because drag comes as a result of friction. Okay, so that's our all forces labeled. Now let's have a look at question C. So the drag lift pulls the skier with a constant resultant force of 300 newtons for a distance of 45 meters. Use the following equation to calculate the work done to pull the skier up the slope. Okay, so work done equals force times the distance, as we covered in the video. Now, some students might see the word resultant and get confused. Resultant really means overall force, because remember, whenever we're looking at work done, we're looking at where did the object overall travel. So if we had an object here, right, so let's take a square, and I have two forces acting this way, both at 5 newtons, oops, and one force acting backwards at 2 newtons. The resultant force here is really found by resolving this diagram. So what we do is 10 newtons this way and 2 newtons this way. So that so let's say that is the negative direction. So what we do is we calculate the sum, which is 10 plus minus 2, which ends up just being 10 minus 2, and that equals 8 newtons positive. So that's our resultant force right there. Always resolve your forces before you start inputting equations, because a lot of people just jump into input equations. Okay, so now let's have a look at the actual equation itself. So that is work done is equal to force times our distance. We have our force 300 newtons, and we have our distance 45 meters, and that equals 13,000. Actually, let's do it in a different color. 13,500 joules. Remember, that's already given in our answer line, but we have to, in case it's not, remember your unit. So 13,500, and that gives us 2 marks. Well done if you got that.